This live stream's beginning is very boring. I'm just getting it set up early because I'm at my house. Hey, cat. Welcome, Maria Lisa. Welcome. I'm really getting things set up. Almost all set up. Since I'm here at my house instead of on campus. My little laptop. Cat scratched. Welcome, Lauren. Welcome. Hey, it's 9 o'clock. Let's give it a couple more minutes for folks to arrive through their notifications, etc. Uh, and we'll get going. Hey, cat. Yeah, come on in. Yeah, get on out. See you later, cat. Welcome, Jacob. Welcome, welcome. Just giving it a couple more minutes as folks find their way to the Zoom zone this Zoomy Tuesday, the 11th of February, here in the year historians call, what is it, the 2025th year of the Common Era. Pat's here with me. I got some sleeping house guests. My little one's going to be on the way near the end of class. but we'll update everybody on that as we go. Hey, welcome, Quincy. Welcome. I knew if I just gave it a couple minutes after the chime of 9, we'd have some folks showing up. Welcome, Ryan. Welcome. Good Zoom morning to you all. Hmm. Our first chat has arrived. Great chat. Excellent chat. Love it. Love a wave. Love an emoji. I'm an emoji lover. They are worth some words. I don't know if they're worth 1,000 words, but some, right? They work. All right, let's give it another minute or so. About 3 or 4 past, we'll get started. Hopefully, we'll have a good group who've made it all the way through all of their notification screens to join us here in this Zoom zone. Uh, thanks. Well, before we get started, I guess thanks again for being flexible on a day when Zoom works way better for your instructor. Mm. And actually, I've got kind of a runny nose today, so maybe now I'm going to get sick. We'll see. We'll see how I feel Wednesday and Thursday. I'd like to be back on campus, but we'll see how we do. I had never had a fever like my kid, and I don't think I have one right now. I have to check. But yeah, all right. It's about 3 minutes past the hour. Let's get into this. Hopefully, we'll get a couple more folks rolling in through their notification screens. Um, we might get some distraction near the end of class. My little one is waking up at his mom's, though she has things she has to do that are going to require him to be over here, likely before our class ends, or maybe like right when class ends. So it might get loud. I might have to run off and take care of a little kid for a minute near the end of class. Otherwise, we're just going to hang out and have a mellow Tuesday morning here, picking up our work after last week's exam. Oh, I have not even looked at your exams yet. The plan was to start looking at them yesterday, but a lot of the because my son was home, I didn't even go to campus yesterday, which was my time to look at exams and start scoring them. So I'm probably going to start that work tomorrow. Tomorrow, I will begin scoring exams, and I have an exam for all 3 of my classes. So there's lots to work on. My goal is to really get a good push going, start on Wednesday, keep going Thursday, and really I can go to campus on Friday and just sit down in the cubicle. I've got some leftover noodles I can take in there, so I have good lunch. Heck, I could take 2 boxes of leftover noodles. Good dinner. And that should be a good day to get a real start on our grading. So expect to start seeing exam grade updates toward the weekend. That's the plan. And otherwise, let's look back at our schedule. I think we're just picking up our discussion right where we left off. So let's go to, I'm heading to content. Oh, and of course, if anybody has any questions about homework or anything else, just let me know in the chat, or just, anytime you can raise a hand or just crank up your mic. I've got my speakers cranked up. So if anyone just needs to get my attention, any of the ways should work. If you do chat and I don't see it, quickly crank up a mic, or if someone else notices a chat that I've missed, crank up a mic and say, "Hey, Ralph, there's a chat," to draw my eyes in that direction. Um, let's see. Let's go down to the old course schedule. If I'm right, yeah, our last topic, well, we talked about it pre-exam, pre-catch-up and review. That was a while back, the first section of chapter 7. Unsurprisingly, our discussion today is about the second section of chapter 7. Oh, and many of you have got your interviewed and have been thinking about, hey, what do I do after my interview to write up my summary? If you haven't, you can always look ahead and read the prompted instructions, but let's talk briefly about the interview summary ideas I've got. And if you have any questions, you can ask now, or of course, you can ask anytime. If anyone's hearing this in the future, you can ask anytime. Let's go check that out. So I'm going to head to our content. I'm going to roll on down to project. There it is right there. Project 3, interview summary. It's not very complicated because since all of you are interviewing different people and you all have different questions to ask your interview subjects and different interests as you're discussing them, um, they're pretty open. So the idea is to write up a summary, at least a page, no more than 3 pages. Even if there's a lot of interesting stuff going on, try to keep it, try to keep your work time down to about 3 pages of thoughtful writing, if that's your style. But about a page or two is the usual length of these. Um, your summary should include just two straightforward ideas. What did you hear that loud sound? I think my cat might be. Please don't. Please don't barf right there, dude. Please don't. Please don't. That's like his like sometimes barking sound he makes. Oh, please no. All right. I begged him not to barf on the floor. Uh, Anyway, so your interview summary should include what you learned from asking both your required questions and your own questions. Ideally, just in your own words, in your own style, just giving a sense of what you got out of the interview and what you've learned about, your subject, the discipline you're heading toward, and how statistics or math fit into those their world as a worker and a person, and the discipline you're headed towards. That's the idea. And that's explained more in number 2, the specific goal of explaining how your interview affected your ideas about how data and statistics are used in your field of interest. Those are the 2 prompts. If you just kind of write a couple paragraphs about each, you will already have a page filled up with thoughtful thinking. Just again, write in your own style, uh, your own format, and should be great. Any questions? No microphones, no little hands flying up in the participants window. I'll give it a couple more beats for if there's a question coming via the chat, just keep on typing. Take your time while I'll navigate to our slides for the day. And if there's a question, we'll talk about that before we get into the discussion. Here I go, slides. Oh, hold on. Yeah, and I've got a drippy nose and a cough, so maybe I'm the next one to get sick. Let's see how it goes. We're heading into chapter 7. I can wrap up chapter 6 in there. Paired data is today's topic. This is kind of a cool technique that kind of builds on the technique we learned about in the last section. So let's go to presenter view and get into it. What is it? What do we mean by paired data? Let's make it clear with an example. Friday the 13th. Between 1990 and 1992, when I was between 18 and 20 years old, researchers in the United Kingdom, UK, collected data on traffic flow, accidents, and hospital admissions on Friday the 13th. Okay, I'm going to stop doing that voice. Researchers collected data on traffic flow, accidents, and hospital admissions on Friday the 13th and on the previous Friday, Friday the 6th. Below is an excerpt from their dataset on traffic flow. We can assume that traffic flow on a given day at locations 1 and 2 are independent. Okay, and see how the dates work there? They have like observations 1 and 2 are both from July 1990. So you got the count of traffic flow on July 6th, 1990 at 2 separate locations. and the week later count of traffic flow at both locations on the 13th, a column calculating the difference in traffic flow. And they're being careful to tell us that traffic flow at location one in the first row, or in all of the light, the odd numbered rows, is independent from traffic flow at location two in the gray rows. And even though they did two measurements on each pair of days, so like September 1991, December 1991, March 92, and November 92, that's how many pairs of 6th and 13th they have, two per month and year. Huh. Kind of clear how that works. Just imagine location one is far away from location two, right? So, but they both seem like busy locations where plenty of traffic flows by. We're talking over 100 and some thousand cars flowing by. I'm guessing they count them with some kind of automatic traffic flow counter system. Cool. So here, wait, I think did I tell y'all I had some family visiting? This is their last morning here, so I'm gonna close this door to give them a better time sleeping. Hey, welcome, Lauren O. Welcome. One more folk in here. Just on time for the beginning of our discussion. We're getting settled into this context of our discussion of paired data. It's about traffic flow at two locations on the 6th and the 13th. Those are Fridays. That's why the 13th is scary sounding in the UK in the early 90s. All right. Oh, and you can notice on this slide too that in every single case, every observation, 1 through 10, there's more traffic on the 6th than on the 13th. See that in the first row, you can see 139,000. Let me annotate to help my eyeballs and yours. This 139,246 cars that flowed by the car counting machine on the 6th of July, 1990, if you subtract away these 138,548 cars counted the following week on the scarier Friday the 13th, well, there were almost 700 more cars that drove by on the 6th. And when you look down the two columns, 6th and 13th, you'll see that in every case, just grab a random one, 8th observation, 124, 631, 120, 249. See there, the difference is larger. Over 4,000 more cars were counted on the 6th than the 13th. So those numbers are all positive, not just because they're ignoring the sign, but because in every case, more cars flowed by on the 6th than the 13th. Perhaps because the 13th is unlucky. We'll talk more about that last idea as we go forward. Okay, but check this out. So researchers wanted to investigate if people's behavior is different on Friday the 13th compared to Friday the 6th. Okay. One approach is to compare the average traffic flow on these 2 days. That's their idea. For a null hypothesis, if there's just no difference, right, between traffic flow on the 6th and the 13th, then average traffic flow on the 6th would be equal to average traffic flow on the 13th, these Fridays. Okay. Alternatively, and our data indicates that it's possible, at least with some values there, average traffic flow on Friday the 6th might not be equal to average traffic flow on Fridays the 13th. Okay, and then each case in the data set, so each row in the data set we looked at on the previous slide represents traffic flow recorded at the same location in the same month of the same year, one count from the 6th Friday and the other from Friday the 13th. Are those two counts independent? Traffic flow at the same location 1 week apart. Think of if you have a commute to Portland Community College of longer than a block, like you have to drive to school. Is your drive, this coming Thursday independent? Is the traffic flow completely independent of your drive last Thursday or next Thursday? And in the chat, no, not independent. Do people get that general sense? Some of the same people are driving to some of the same places week after week. So traffic is dependent on a lot of conditions in the local community, right? Who works where and when. If there's road construction that lasts a few months, that would slow down traffic for a few months. Uh, yeah, taking exactly the same route every time, and that's very popular. Yeah, unless there's some reason to be detoured by construction. Yeah, so there's same people on the same roads day to day for similar reasons. Things do shift over long scales of time, like before 2014, I almost never drove to Sylvania campus. But then if you went back to 2003, I did drive to Sylvania campus a lot because I was a student. But you know, things were different in 2003 and 2025 driving from here to Sylvania, but week to week, they're pretty dang similar. So yeah, two counts from the same location, 1 week apart, are not independent. And this is generally true. If you observe the exact same thing a certain amount of time apart, especially a small amount of time, you're kind of in a before and after, or this time, that time that are consecutive setup. That's just a natural pairing of observations. Things just aren't independent like that. So cool. Good. Uh, and since whenever we want to look at comparing averages from two separate groups, like back when we looked at them for proportions in the previous chapter, it was important that the groups be independent of one another. Here, we don't have that independence, so the researchers simply look at the pairwise differences. We already had that column in the data set, and that's where we're going to focus for doing inference and for figuring out a p-value to analyze these hypotheses. Click. See, analyzing paired data with two observations for each case that are not independent. These data are paired. It's incredibly obvious that you have paired data as soon as when you're thinking through the data set, especially if you can't see the spreadsheet, when you know that there's two numbers in the same row, right? They are truly paired up by date and location, at least not the calendar days, but the months and the years and the locations pair them up across the thing. When that's true, researchers focus on analyzing their differences. This works for other kinds of before and after data. Data comparing experiences of people who are like maybe partners or like a parent-child pair could be analyzed for something. There's all sorts of places where there's real relationships and you still want to examine the difference between the two people or things that you are observing. Paired data happens in lots of research settings. Now, to analyze paired data, researchers often look at the difference in outcome for each pair of observations. So that's our diff column down there in the data set. And here, they're just making it completely explicit. I mentioned this before, but in every case, that's the traffic count on Friday the 6th minus the count on Friday the 13th. They're all positive because, yeah, it's always a little higher on the 6th than the 13th. Perhaps due to bad luck on the 13th, then people realizing I should stay home to avoid being hacked to death by a monstrous masked killer. Oh, pardon me, content warning, horror movie references today because of Friday the 13th. The voice is terrible. One of my house guests loves horror movies, so they're on my mind, not just because of the name of the slides. Oh, and just to note, whenever you're doing subtraction in any kind of analysis and you're using some subtraction results, always subtract using a consistent order. You would want positive differences for, like we have here, whenever there's more traffic on the 6th and the 13th. And of course, if in any observations it went the other direction, you'd want a negative difference so you could understand when that's happening. Consistent order for subtraction is just a crucial, meaningful piece of analysis. The more I talk, the more I think I'm going to be more confident that I'm sick today. Okay, every time we meet these inference methods, we have a little slide called parameter. That's our population characteristic that we'd like to learn more about using statistics. And we've got our point estimate, which is what we can calculate and estimate from our sample data, usually our statistic. Here, the parameter of interest is the average difference. See the phrase, the average difference. So if you think of the taking all of the diffs down that column, do I have the column here? No, they don't. All of the diffs down that paired differences column, it's their average. The parameter is not just for these 10, of course, that's for all of the locations that are at least comparable to location 1 and location 2 in the UK. So mu, Greek letter for mean of a population, subscript diff for mean of the differences. Cool. That's what researchers are going to focus on in the abstract for making assumptions and for attempted estimation. And then the point estimate, their statistic, is just the average difference between traffic flow on Friday the 6th and Friday the 13th for the sampled locations, the 10 we saw on the previous slide. Sample mean X bar of the differences. Maybe I'd read that mean of the sample differences or sample mean of differences. All these sentences get longer, but the subscript diff just means focus your attention on that differences column. It's X bar sample mean of those 10 differences we've got. Whew. Okay. Now the cool thing here is um, hypotheses wise, we already stated them quickly on a previous slide, but the idea here being, if in fact there was no difference between the traffic flow on the 6th and the 13th as spelled out on a previous slide as a null hypothesis, what should the average difference be? So if one of the locations, it was sometimes a little higher and sometimes a little lower and sometimes close to nothing. And at the other location, it was sometimes a little bit of a bigger difference one direction, sometimes the other direction, sometimes no difference or really close to no difference. If there's really no difference in traffic flow on the 2 days, generally, what should the average difference in flow be? I'm with Lauren R from the chat. Yeah, 0. If there's no difference between two numbers, well, you subtract one from the other, you should get 0, a difference of 0. Cool. And that's going to be a lovely symbolic null hypothesis. So no difference on average would give us the average difference of 0 in the whole population. So hypotheses wise, now they just want to focus our attention on the symbolic version of the stating our null and alternative hypotheses. What are the hypotheses for testing that the average difference between traffic flow on Friday the 6th and 13th is 0? And that's in this paired situation. Rather than have everybody type on Zoom, let me just, we've already got a good idea coming in the chat. People like option C. I'll just look at all 4 of them and tell you why the bad ones look bad too. And then we'll double check your option C idea. First one, mean of counts on the 6th equal to mean of counts on the 13th, that's not good. They didn't pair them up, so they're not talking about differences here. A's bad. Uh, Second option, P, that's for proportion, not mean. Sorry, no proportions here. And they also make the same issue with 6th and 13th. They're not paired up. B looks bad. C, as suggested by Quincy and Lauren R, mu, mean of the differences, set to 0. That follows if the average traffic flow on the 6th is equal to the average traffic flow on the 13th. That would be right. And alternatively, they're not equal to each other. That's great. No one ever mentioned a specific direction for this in any of the statements we've seen before. C is correct. Looks good. And D looks bad, just in case it was drawing your eye, because it does have the diff in there. It's because they're talking about the sample mean. And we don't talk about samples in or sample statistics in the hypotheses for hypothesis testing. There is a note here. The most attractive incorrect selection here is the first one, because it does reflect some of the language we saw on that previous slide. Let's assume the mean on the 6th of traffic flow is equal to the mean on the 13th of traffic flow. See the subtle difference here in the language? Option A here looks at the difference of the averages. That would be if we felt comfortable considering flow on the 6th and flow on the 13th as independent. If those are independent kind of sets of observations, they're not. We're looking at the average of the differences because of the pairing. We'll look at places where options like A make sense and statements like that make sense in the next section. We'll talk about inference for the difference of means or difference of averages, but they have to be from two independent groups. Here in the paired world, it's the average of the differences we care about, so we get that mu subscript diff. Mellow. Oh, let me get all my messy notes out of the way. Okay, now what's cool here is the calculations, again, are going to use the t distribution. Same distribution we used in the previous section when we studied inference about one population mean. So we're going to be able to use a t-test for a hypothesis test or a t-interval for a confidence interval that would estimate the mean difference out in the population. We do the inference using the mean of one sample. That sample's just the differences. And we test to see if the mean difference is not equal to 0. So no new techniques here, no new tests to learn about, no new distributions. Everything works just like in the previous section, except for that first step of focusing our attention on differences between pairs. That's all. That's the only really new technique we're looking at here. Kind of cool. So here in the Friday the 13th world, there's the whole data set. There are the sample statistics for the differences right there. You can see we've got the mean of the differences, x bar subscript diff, rounded off to the nearest difference, or sorry, difference in traffic flow is 1,836. We've got the sample standard deviation of those differences in traffic flow, S subscript diff, 1,176. And a reminder, we're looking at 10 values here. Kind of cool. Pardon me. And those are all three of the numbers we need to get the p-value calculated, either using analytical tools like formulas and our calculators, or using a computer and friendly computer software like GeoGebra or any other good working stats software. Let's see which option our slides like best for our first try. Oh, slow down, Ralph. I'm talking about calculations before I check the conditions for inference. Once we've got those hypotheses set and we know that it's going to be a t-test or a one a t-test for one mean, we got to check the conditions for inference. Um, Same conditions as we had back in section one, except with the slight wrinkles of things being about differences instead of just sample numbers. So assume this can be considered a random sample of differences. They're giving us that as a gift right here. And then sample size and skew, the second check. Well, here are the 10 differences graphed uh, on a little histogram. What do you think? 10 is less than 30, so it is a small sample of differences, but does that look, you know, can I show you what my eyeballs are seeing there? Look at this. If I think about I can imagine that that's just because that's just one difference out here. The bulk of them have this nice unimodal symmetric look. Bulk of them. There's another way to check this with what's called a normal quantile plot. That's a little more involved. We'd have to open up a spreadsheet that works for small samples. We'll talk about that later in the quarter. But that looks pretty good. Yeah, sample of differences does not look wildly skewed away from a mostly symmetric graph. Cool. Let's assume the population of differences may well be normal. If it's safe to assume randomness here, we can assume the data are independent and that no difference in traffic flow directly impacts another. Cool. Oh, calculations. Let me do these. Let's do these by hand. I'll show you how I get these calculated one step at a time. So back here, when we've got these three stats, I'm just going to type them up so I've got them. X bar diff. Oh, like underscore. X bar diff. I should have written these down before. 1836. This is just how I do homework too. When I see these numbers in a textbook or on an exam, I just somewhere in my notes where I'm working, I type them all out so I've got them. And that way, when I want to go use technology for my calculations, I've already got my numbers there. I don't have to flip back and forth a bunch. So here I go over to GeoGebra. Oh, let me take the smart path. Our our course links. We've got our direct GeoGebra classic link right there, third one. Probability for doing calculations for a hypothesis test. Been a little while since the exam. Hopefully people got to relax your statistical brains over the weekend, but we don't want to forget to be on the statistics side of GeoGebra. And we don't want to forget to set up the correct routine right here. And I've got to get something out of my way on my screen that you can't see, but it's bothering me. Z-test of a mean. That's a test of a mean, but notice in the sample, you've got a sample mean. That would be an X bar, but that's a sigma is the Greek letter. That's population standard deviation. We certainly don't have that. So we want to be sure to do a t-test of a mean. T-test. And when we land there, pretty relaxing. Our null hypothesis was assume mu diff, or the average difference in means is 0. So dump that into the null hypothesis. Alternatively, it was just there could be a difference here. Sample mean, we've got it right there in our notes, 1836. Sample standard deviation of the differences, 1176 with 10 observed differences from jolly old England. And there you go. That is a nice, quick, straightforward calculation. If you're curious about the T statistic, so how far out into the tail of the student T distribution you'd go, 4.9. Well, that's 4.9 standard deviations in that bell-shaped curve. That's far enough to get you a p-value. There's only 8/10,000ths of the area in the curve, under that curve, pardon me, further than about 4.9 standard deviations away from that center in both directions. 0008, low, low, low p-value. Yeah. So let's double check that I did this right. I'll check my calculation with that slide I have in here. Conditions are good. 0008, calculation good. Just I made the slide. Why all this animation? What's it for? We've already done this. We got the null and alternative hypotheses. Oh, there's more notes. Always typing those out myself. And then the output's the crucial thing. Test statistic, 4 9/10 and a little more. And the p-value very far below all of our classic significance levels. Like it's well below 1%. Heck, it's 0.08 of 1%. 0.08 of a percent. That's pretty low. That's low, low. Sheesh. Hold on. If we want to find that test statistic by hand, if you do like to get something out of these techniques just at the human rate, the test statistic for inference on a small sample mean, well, everything works the same as it did in the first section of chapter 7 here. The test statistic, capital T, is our notation in our text. Subscript with degrees of freedom for the proper degrees of freedom for the student T distribution. That's always going to be one less than the number you're working with for this one sample method. So here that'd be 9, 10 differences minus 1. You just take your point estimate. That's your sample mean of differences. Subtract the null value. Super easy subtraction here because we've assumed a difference of 0. And divide through by the standard error, which is calculated with a ratio of sample standard deviation and the square root of the sample size. They're rounding off these numbers in their process here. They come up with a t-score. Look at that. Rounding, it's just a little bit different. Is it the same as ours if we round ours off? Oh yeah, if we round ours off, we get 4.94. With all their rounding, still 4.94 rounded to the nearest hundredths. Got our degrees of freedom right here. They go into do they head into let's see how they get their p-value. Oh, well, there it is. A picture of it in GeoGebra. If you take your degrees of freedom, oh, that's a bad picture. If you take our degrees of freedom 9 to our student T distribution, so I'm here on the distribution side. There's the student T distribution. Degrees of freedom 9, that's the shape for this particular example. Looking out beyond in both directions, both tails, p-value in one direction negative and p-value in the other direction positive. What? I'm right. I wrote that wrong. Sorry, it's 4.94 t-score. T-score, Ralph. T-score 4.94 rounded off. See that? There's that t-value to the nearest hundredth. Out in the tails, you can see the tails here in the picture. It's almost all the way off the screen in my GeoGebra window. That gets us a tiny, tiny area in each tail, adding them up for the p-value of yeah, only 0.08 of a percent. That's the modern way to get the p-value from the t statistic. In olden times, people might use a table in the back of a book and a more complicated method. But a little picture on the slide of how that looks too. Okay, there we go. Fairly high t statistic, very low p-value. Null hypothesis was there's no difference. Sorry, there's the average difference in traffic flow on Friday the 6th and Friday the 13th in the UK is 0. Or there's no difference on average in traffic flow on the 6th and the 13th. So what do we conclude here? I'll leave that to you all to either use a mic or a chat. What would your conclusion be in this particular setting? Well, I just cough and feel bad. Oh no. It's not home. If you want that null hypothesis, like in words, I can go grab it from that previous slide. That's the best thing to have near you when you want to make a conclusion is the null hypothesis and the alternative, spelled out in plain language. Should we go grab those back? Will that help us with our conclusion? I'm going to go grab them for me. I'm going to go back past the symbolic version all the way to the slide where they first said, it was way back there. There they are. Those are the original null and alternative hypotheses. Let me just grab them for my notes here. Copy. Oops, oops, oops. How about that kind of slideshow? This kind of slideshow. Oh, great. We've got an idea in the chat right as I bring these forward. Let's compare it all and we can see it all together. A very low p-value. Our hypotheses were, let's put them down here at the bottom of the slide. Average traffic flow on this Friday the 6th is the same as average traffic flow on Friday the 13th. Remember, P is low, null must go. And we've got a thoughtfully phrased conclusion in the chat there. The average traffic on the 6th and 13th is statistically different from each other. Yeah, we have statistical evidence of a difference here because we're rejecting the assumption of no difference. Great. Let's see how the slides put it. Reject a null. Yeah, so there's my P is low, null must go. There is evidence that the mean of the differences is not 0. That's evidence traffic flow is not the same on Friday the 6th and Friday the 13th. There we go. Getting intense here, Friday-wise. Hmm. 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 We say as we consider the evidence about traffic flow on 2 days of the month. Okay. Oh, hey, oh, well, what is the difference? Well, we just did this hypothesis test. It's a nice hypothesis testing example. But even all the way back at the beginning, when we looked at the data set, I could see with my eyes that all of the differences were positive. So even at that step, I might have been wanting to ask, what is the difference out there in the population? Can we estimate that with a confidence interval? Like put a little margin of error on our sample mean of differences? So, but the other way to look at this is if you go ahead and do a hypothesis test and you've got evidence of some kind of a difference, hey, why not estimate that difference with the confidence interval? Give it a little margin of error and give people a sense of what the data shows you about your population. Good old confidence intervals. Relaxing, confidence interval. And it's the same idea because we have 10 differences and we have the t interval for a mean or a t estimate of a mean in the words of GeoGebra's description. Great, we can just do this calculation with the student t-distribution and some technology. Reminders of how they work, confidence intervals in general. We're always going to have our point estimate. Here, that's our samples difference in means. Sorry, samples mean of differences. And we got to add and subtract a margin of error based on how confident we'd like to be. That'll give us a critical number called T star here, along with the standard error, which estimates how we would expect things to vary from sample to sample using sample statistics. Yeah. Oh, I could have showed more stuff on the slide as I was talking. That's all the stuff I said, but just typed up. Critical number based on confidence is T star. Standard error estimates how things should vary from sample to sample. Together, that product gets us the margin of error. Constructing by technology, we've already done most of the work over in GeoGebra. We just need to switch to a t estimate of a mean. That's the routine. So if I'm in the statistics side here, I've already got the mean from the samples differences, their standard deviation, and the sample size. Just switch it over to t estimate of a mean. Make sure my confidence level is what I'd like it to be. I think I was going for 95% here. Yeah, 95% is good. And then the margin of error ends up being about 841 fewer or more cars on the road, compared to our samples mean. It's really hard to use the units here because they're all about differences. A difference of 841 is the margin of error. Subtracting that and adding that to the estimate, we get our lower limit and our upper limits. And those are both positive numbers. So the confidence interval also shows evidence of a genuine difference here, as low as about 995 more cars on the road on the 6th and the 13th, and as high as about 2,677 more cars on the road on average on the 6th than the 13th. Hmm. 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 Our slide has all the tips to get through all that calculation if you're starting it from scratch. So just don't forget, beyond the statistics side, use that t estimate of a mean when you're working with these paired values and studying their differences. Cool. Great. The way the slides go at the by hand calculations, they just want to double check that we're good at getting the standard error calculated correctly. So which of the following is the correct calculation? Oh, and also we need to make sure we get the critical t-score correct. So which of these three options would get us the correct 95% confidence interval here? Let me use my eyeballs on this one. I can see one of them's I can see a couple of them are obviously wrong. Let me just help you out because this is newer to most of you. Where's my no good? Oh, they're all good for the sample mean of the differences, 1,836, no problem. But option C here is bad for the standard error. It's not just the standard deviation, 1176. It's got to be the 372. That's the 1176 divided by the square root of 10. Knocks it down to almost a third. So A and B look good there. Then between A and B, they've got two different choices for the critical number. Remember to double check the critical number. You want to go to the student t distribution. Let me show, yeah, which one of those is right? Let's just double check it. Is it going to be 196 or 226 for the critical number? Let's go peek over at the t distribution and get a sense of which one of those is correct. So to check a critical number, again, I want to be in the distribution world. What I want to see is right here in the degrees of freedom 9 world, I need to know, let me just draw my little sketch here. For my critical number, I need to know which in this bell, I'm staring at the bell on the screen while I draw in hopes of drawing a beautiful bell. Yeah, I want to get 95% of the area under this bell in the center. So there's 95%. And my critical t-score, t star, will be the upper cutoff of that central 95% of area. So, and for GeoGebra, I can't just directly put the numbers for the tail cutoffs, get them back from the area in both tails. But I can focus in here on this area, the area in the upper tail. I can do that using GeoGebra's upper tail function. I can type an area right there. So that's going to be what? If I've got 5% remaining in both tails, right? Where's my pen? See, there's half of that 5% there, half of that 5% there. So that's going to be, yeah, the remaining 5%. Knock that down by half, and that's going to be 2.5%. So get down to the hundredths for the 2%, and then a 0.5% more. That's the number that I dump into my percentage to get me my critical number. And that's, yeah, 2.26 rounded off to the nearest hundredth. So I get 2.26 from my. And the more familiar you get with, I mean, if you get more familiar with these curves, the tails of these student t distributions are bigger than the normal distribution. So we get a little bigger critical number than we would at 95% confidence with the normal distribution. So when I head back for my, put my drawing in the worst possible place. Let me move that over. Maybe right there. Hi, friend. Oh, whoops. Ah, yeah, they've got the B 2.26. That's our critical number. There's 995 of the 2,677. Their boundaries, yeah, 995, 2,677. Same boundaries we got from GeoGebra with their method. Remember, again, sometimes when you're doing the methods we use with technology, wherever you round off, there might be off by one with the textbook's results because the textbook often uses an older fashioned technology, the table in the back of the book for various parts of these tasks. Cool. All right. So there looks like a very positive difference in traffic flow between Friday the 6th and Friday the 13th in early 90s United Kingdom on, I'm guessing, major thoroughfares. Okay, we're learning stuff. Bye bye, little sketch. Confidence interval interpretation. It gets wordier and more challenging to write these out when you have more complicated situations here. Like they've written down their symbolic confidence interval at the top, mu subscript diff sixths minus 13th. I think that's short for the mean of the differences in traffic flow on Friday the 6th and Friday the 13th. And then just the boundaries of their confidence interval. Uh, you want to sort out with your eyeballs which of those looks the best to you, A, B, C, or D. Throw it in the chat. We'll get some agreement, and then we'll take our break after we've got this little interpretation done. I'll help you all out. I noticed two of them were bad for sure. Uh, okay, we've got a suggestion too. All right, cool. Here, let me get rid of the definitely bad ones. B is bad. On Friday the 6th, there are 995 to 2,677 fewer cars on the road than the 13th. No, those numbers are positive. That indicates more cars on average on the 6th. And C is even kind of weirder and worse. On Friday the 6th, there are 995 fewer, 2,677 more. No, again, it's more and more. So that's bad. That fewer shows up again there. The positive numbers indicate more cars on average on the road on the 6th. D, let's check it out. That's our suggestion. On Friday the 13th, there are 995 to 2,677 fewer cars on the road than on Friday the 6th on average. I like it. Let's give that one a check mark from the chat and a check mark from Ralph. And let's peek back at A because I think that's the one. It looks so similar, but let's read it. We are 95% confident that the difference between the average number of cars on the road on the 6th and the 13th is between 995 and 2,677. That one is just subtly bad. It's so subtle, though. Only statisticians and stats teachers would notice. This one, well, I'd say that the average here, fewer cars on average in part D, the one that Lauren R. and I like, that one is saying in language mu subscript diff, uh, you know, not zero, right? For the fewer cars, right? Um, if you're a nerd who pays attention to semantics, careful word choice, you might notice that on part A, the average number of cars on the road, mu, they're saying on the 6th, so subscript 6, and the difference between the averages, mu subscript 13th, not zero. And that's not the one we're doing here. That's the one that if the 2 days were completely independent, not paired, that would take us to A. But that I would, if either one A or D was written on your exam, and this was a question on an exam, I might like put a little note if I was wide awake that like actually you want to be careful to focus on the mean of the differences. I might write that note for part A, but I would never mark it wrong because it's someone doing their dangest to like actually communicate what's correct, even though they're wrong. So this would be like wrong because it's difference and the and puts us up in that situation. But it's so subtle. That's so subtle. Um, if you just focus in on saying what you mean here, fewer cars on the road on the 6th and the 13th on average, put it in the plainest language you can, you'll end up with a good interpretation. But it can be tricky when you're comparing two groups and talking about a difference and an average. The language can get a little hard to get your writing ability around. Uh, I'd be willing to bet that ChatGPT writes these worse than people who are just learning about it because I bet they'd make that mistake number A with a so-called artificial intelligence would make mistake A as often as they would get it right because it's a subtle sort of human perspective here, not an easy to go plagiarize all the work of previous statistics students process like plagiarism machine does. I mean, sorry, stealing people's ideas machine does. It's not really plagiarism when you're just directly stealing people's creative and academic work. That's just stealing. Uh, anyway, cool. It's 10 o'clock. Great work on that confidence interval. Let's peek at the next slide just so we know what's there. Synthesis. That'll be perfect for after the break. We'll synthesize things after the break. Let's go get a 10-minute relax. I'll get a personal break and a fresh hot drink, I think. And y'all do the same, whatever is best for you in your break world. We'll be back here at 11 minutes past the hour. See you soon. about a minute left in break, and we're pretty much back. We got a hot drink. We got a water. Didn't have time to call my co-parent to double check on when the little cat's gonna show up. The not fuzzy cat. But should be any time between now and 11. Well, we'll just see how it goes. Okay, let's do some synthesizing. Here we go. Does the conclusion from the hypothesis test, that was, we have significant evidence that the average difference in traffic flow on Friday the 6th and Friday the 13th in the UK is not zero, so that there is some difference on average in traffic flow. Does that conclusion agree with the findings of the confidence interval? That's where we estimated with 95% confidence in our estimate that the average difference in traffic flow on Friday the 6th and Friday the 13th in the UK is somewhere between 995 and 2,677. Do those conclusions align? Do they make sense together as a pair of statements? Does the question make sense? Does the question even make sense what they're asking? Evidence of a difference and an estimation that the difference is between 990 something and 2000 something and something. Do those align? Are those agreeing? Conclusions. Hmm. Pat, what are you doing, buddy? Hmm. Well, here, let's see what this. Yeah, yes, yes, yes. Okay, exactly. So if they, let's put it this way, if they didn't agree, the confidence interval's boundaries would have to be very close to or even include zero, right? Because we rejected a difference of zero, and, and zero is not in the confidence interval. So that's agreement. Difference of zero doesn't make any sense in either setting. So yeah, how'd they put on the slide? Yes, hypothesis test found a significant difference. That's rejecting a difference on average of zero. And the confidence interval does not contain that null value of zero. That's the basic idea in general. When your null value gets rejected and your confidence interval does not include it, you've got agreement between your two methods. Likewise, if you do not reject a null hypothesis value and it is in your estimate, your confidence interval, then they're agreeing. This happens most of the time in most data sets. The only times they disagree when you've done everything right is when things are kind of like right on the edge, like your significance level is 5% and maybe your p-value is like 0.048. And then maybe, you'd reject that null at 5% significance, but the way that things work out, maybe your null does end up at the very edge of your confidence interval because of some math stuff. But generally, they're going to agree like this. Okay, here's my question. So in both cases, hypothesis test and confidence interval, we're saying we don't think that the average difference in traffic flow, I mean, we have evidence of a difference in traffic flow between the 6th and the 13th, that there's more traffic on the roads of the UK on average on the 6th Friday than Friday the 13th. Do the findings of this study suggest that people believe Friday the 13th is a day of bad luck? Why or why not? Good in the chat. No way to conclude that from Quincy. I'm with you, Quincy. No way. Now, why not? Can anybody put that in a sentence they're either confident just typing into the chat or sharing on the mic? There's tons of ways to think about it. So we'll talk about it, whatever ones y'all come up with, plus whatever ones I come up with. Ah, there we go. Okay, good chat from Quincy again. Driving habits can be altered due to many different reasons. Superstition, wherever, yeah, not being on the top of the list, at least not for most people, right? Uh, I don't know when people got their paychecks in early 90s United Kingdom locations uh, near these traffic counting stations they installed for their research. But what if people get their check like on the first of the month and then they get paid again on the 15th of the month? People who are living on a tight budget would have less money for petrol, as they call it in the United Kingdom, to fuel their cars. It might make sense to cut down on your driving if you can't afford that next tank of gas until the 15th. That's just the first thing that comes to mind. Uh, Also, like, no one's asking anybody about if they're staying home or not for bad luck reasons. There's zero superstition variables in the data set. This is an attempt at like a proxy measurement based on behavior. Those almost never work, and they almost never tell the whole story. Um, can anybody think of a way they might try to see if it's about Friday the 13th? Like what kind of research technique you would need to do to get a sense of if it was? Now, there's definitely a survey of people. A survey might work. What if you wanted to just stick with proxy measurements? You wanted to just count traffic. How does my idea sound? What if you also counted traffic at those locations, not just on Fridays that are the 6th and the 13th, but also the 5th and the 12th, the 7th and the 14th, whatever, the 1st and the 15th, the 1st and the 8th. If you count it different Fridays, and heck, maybe try Thursdays and Saturdays, like nearby in similar months and times, you might see that there's an actual trend near the 13th. And even still, you'd still have to have a survey to back it up with some actual feelings and superstitious beliefs among people in the UK. It does really make me want to count a lot of cars driving around the UK. Or not. I'm fine with people not knowing just how much superstition impacts our driving. Less accidents? Should there be less accidents because people are superstitious? Would they be more careful? But that's another proxy, right? See, it's all proxies. It's the survey that Quincy's describing in the chat. That's just how you could understand people's actual levels of superstition and get some sense of if their behaviors they describe in the survey match what you see in reality. That's how you'd set up a thoughtful observation. You'd want to get a sense of what to look for, then go look at it. Not the other way, like these folks did. Bad research, friends. Let's see what the slide says. No, this is an observational study. Yeah, we have just observed a significant difference between the number of cars on the road on these 2 days. Yeah, there's no causation here, especially not with related to their beliefs, because there's no test or measurement or observation of people's beliefs. Weird study, but this is a common thing. People often do proxy measurements using whatever data is available, especially in a lot of observational studies where you have some data and you'd like to understand something about people. Sometimes, I know in education at least, sometimes my colleagues and me, we will look at like success rates and things like that, but it doesn't get at the questions we're asking in the same way that a survey that is detailed and thoughtful might get at it, because we often don't know the right questions to ask. Like if we're trying to decide whose exam strategy is a better exam strategy, just looking at pass rates doesn't really tell the tale as much as understanding what actually works best for students and their learning, which grades doesn't really talk about. Grades are just how we rate things, and from our perspective, it's not how students really learn. Yeah, and there's that straightforward example. Observational studies only make correlations, right? So there could be some correlation here. If you could measure, if there was some observation of their beliefs, maybe there is correlation between people staying home, but we don't have it here. Um, and yeah, I don't know how you'd set up an experiment to talk about people's superstitious beliefs other than really weird, scary things that you'd have to have a lot of power to do. Oh, like how social media companies experiment on us all the time to get more money. Okay, let's see what else we've got here. Another example. This one's cool too. Straightforward when we pair things up and how. 200 observations randomly sampled from the high school and beyond survey. 200 students took a reading and writing test. So a reading test and a writing test. Separate tests, one for reading, one for writing. Their scores are shown below. Are the reading and writing scores for each of the 200 students independent of each other? So they mean for student number 1, that's this person, is their reading score independent of their writing score. For student number 4, is their reading score independent of their writing score. All the way down the list to the last student is student 200's reading score independent of their writing score. Yay or nay? No, kind of an obvious answer. Reading and writing are intimately connected skills. People who do more writing tend to develop their reading skills more, and vice versa. People who love reading and read a lot tend to have that strengthens their writing skills. People who just get some crappy junk off ChatGPT are hurting their reading skills and their writing skills. Research is coming on that soon. I've already seen a few research results starting to dribble in that stuff just hurts our brains. But it makes money for some jerks, so it's worth it. And oh, no, just like the chat, they even put an exclamation mark on there. And looky there, they gave us a graph in. There's the differences in now a gray column there. They're not all positive. 3 of the students we can see have a higher reading score than writing score. See there on the graph, you can see it's reading minus writing. So a positive difference is like that 57 is 5 greater than 52. 3 of these students have positive differences, higher reading scores. 2 of the ones we can see have higher writing scores. And when we look at the graph, maybe a little more than half of them got higher writing scores. It's just the histogram is slightly skewed below 0, but not that much. It's fairly symmetric, fairly unimodal. Looks like a normal set of differences. Pretty random looking. Kind of cool. Okay. Paired observations. Again, when this idea is new of pairing things up, there's the 2 ways we can think about the differences we see in average reading and writing scores. We could ask, are the average reading scores the same as the average writing scores? in that case, on the left here, we would look at this picture and ask ourselves, is the mean score here, I'll use the median from the box plot, similar to the mean score or the median over there, looking at reading scores and writing scores as separate groups. Um, that's that way. Or we could ask, on average, are students doing better at reading? That's this half of this graph, based on the differences, or on writing? That's this half of the graph based on the differences, on average. In this case, we are looking at the differences, and that relates individual students' scores to one another with simple subtraction. No surprise, we're not in this situation. We just said these are not independent, so we shouldn't divide the scores from one another. We are over here in the world of paired differences. It's not just the name of the slide, it's the name of the whole section. When there are, like, if it was a totally different group of students taking reading and writing tests, we could compare them as independent groups with techniques we'll learn about in the next section. Yeah, so we'll stick with the paired differences here again. Here they've got them, the observed average difference between the two scores. So observed average is an X bar. Between the two scores difference is a diff. That's negative 545 thousandths. So I was right. It's a little further toward the negative direction in the picture. And the standard deviation, S, of the differences is 8.887 points for these n equals 200 students. Do these data provide convincing evidence of a difference between the average exam scores on the two exams? Well, the null hypothesis would be no difference on average between reading and writing scores. Yeah, and then the alternative, yeah, there's a difference. And they're saying use that significance level, 5%. Well, before we do the calculation, and we want to not make the mistake I made in the first half of class, do these data meet the criteria, the conditions for doing this hypothesis test? Looking back at the previous slide, we can see the differences. Well, we've got 200 of them, right? So there's well over 30 differences here. Plus, it's probably safe to assume the population of differences, like all students' differences in these two scores who are comparable students, would probably be fairly unimodal and fairly symmetric. Big sample plus the population should be fairly unimodal. Sample size and shape are great. The other question for the conditions is, let's go back to the description of who we're working with here. 200 observations of randomly sampled high school and beyond survey takers. 200 students randomly sampled from, I'm guessing, a large group. Is it safe to assume that the differences are independent from each other? So the students' differences in scores are independent from one another. That's the crucial independence of the data check. Like, yeah, all right, they're in the chat. Great. Lauren R.'s got it in the chat. We've got randomly sampled students. So yeah, we can safely assume their differences in scores are independent of one another. I mean, they might be dependent. Imagine if they just taken, if the 200 students were from exactly 4 classes of 25 students, and those 25 students were doing the same kind of reading practice and writing practice for a whole year before they took the test. No randomness, like a convenience sample or maybe a cluster sample that's bad, right? Where they're not accounting for the differences in the other hundreds and hundreds of classes of students. So yeah, random sampling should get us independence though. So we're in great shape. From there, with those two checks done, we can just go do our t-test for a mean. And again, our null hypothesis, no difference on average. It's going to get us the same exact when we go to the t-test world. So let's head to t-test of a mean here and get my notes where I can read them better. No difference on average. So the mean of the differences we're going to assume is zero, just like before. That's pretty much always the null hypothesis assumption in this paired differences world. I'm just going to change my statistics here to be like my notes. Negative 545 thousandths for the sample mean, 8 and 887 thousandths for the sample standard deviation, and 200 students for the sample size. Mellow. Let me just grab, well, we'll just leave this slide here. We've got a t statistic, a test statistic that's not even as big as -1. So we're within one standard deviation of the center of our t distribution. That gets us a p-value if we look at the area out in both tails. That's over 35%, at like 39% if I round off to the nearest whole percentage. 39%, that's a pretty big p-value. Okay. Let's go back to the slides and see how our slides makers work through it. Oh, cool. They got the notes. What's going on here? Oh, they're doing the by hand work. T-test statistic. They're taking our sample mean, subtracting away the assumed difference of 0, straightforward, dividing by the standard error calculation. With the node, our degrees of freedom is 199. There's that test statistic of -87 hundredths. Oh, there's their note data of differences, approximately symmetric with no outliers. We looked at the graph too. Their p-value, they come back at 39% or so if you round off. They got their 1949 from a different place than we went to our graph to get our p-value. That's fine. P-value is huge, well over 5%. So we're not going to reject the null hypothesis. And no evidence here of any difference on average between reading and writing scores for these students, or students in this population from which these ones were drawn. It's kind of cool. So yeah, the tests are set up to kind of match outcomes for reading and writing. May be helpful if you can use those test scores to help identify students who need either more challenging material in school to like really take full advantage and offer them full creativity and development if they're really strong at reading and writing at their age. And if for students who are developing those skills, hopefully the test doesn't just label them as failures, but it gives teachers an idea what kinds of supports could really help those students really develop their reading and writing skills in the most, joyful, creative way possible. Hmm. Oh, which of the following is the correct interpretation of the p-value? Let's read these. There's a lot of stuff here. A, probability that the average scores on the reading and writing exams are equal. I'm going to put that in plain language. That's probability that null hypothesis is true. Plain language there. Simplify it. B, probability that the average scores on the reading and writing exams are different. That'd be the probability that the alternative hypothesis is true. Put in plain general language. C, it's a paragraph long. probability of obtaining a random sample of 200 students where the average difference between the reading and writing scores is at least 545 thousandths in either direction, if in fact the true average difference between the scores is 0. Let me see if I can get that into general language like I did the first two. Probability of seeing these data under assumption null is true. That's pretty close because they're talking about obtaining a random sample and seeing a statistic like they see under the assumption the null is true. Kind of long. And the last one, probability of incorrectly rejecting the null hypothesis if in fact the null hypothesis is true. That's probability of type 1 error. Okay, you've got those now, both in the specific language of this, well, most of them in the specific language of this research we just looked at, also in some general language. Which one of those descriptions is closest to the actual interpretation of a p-value here in our lives? Remember, interpreting a p-value isn't just rejecting or not rejecting the null. It's the more complicated idea of what the probability means, right? So which of those captures the actual, what does the probability given by this p-value tell us as a number? Hey, we got a vote. We got one vote for 2 votes. Hey, I love it. Great. 2 votes for C. Good. It is C. It's the complicated one. Um, the first one there, just both the first and second, they only zoom in on one of the two hypotheses. That's not how it works at all. As we look at the complicated logic of hypothesis testing again and again this quarter, I hope it's becoming more and more clear that when we get this p-value, it's only there because we made an assumption about the population and used sample data to calculate, well, how likely would these data look under that assumption? That how likely, that's our p-value. So I'm not even going to bother with that. D is just a weird distractor, but it's the complicated relationship between our sample and our sample data and our assumption about the population that generates the likelihood of a p-value. The more that complicated idea starts to feel like it makes some sense, the more statistically literate you are. The deeper you can get that understanding in our remaining weeks together, the more happy your psychology program, your business program, your program in the medical fields, or any program you're working toward will be when you're out there in your discipline, when you're reading research. If you hold on to that idea, you'll have a real leg up on understanding more than people around you. Like people who only take one statistics class, for example, often don't get enough time to really digest and understand what a p-value means. And their eyes tend to just glaze over when they see the letter P in a research report. Whereas once it actually makes sense and is kind of an internal part of your knowledge base, that letter does make sense when you see it in context and you can think about it. And that just gives you more ability as a thinker and an analyzer, which is cool. Of course, it's a different amount of development for all of us this quarter, how much we internalize and understand the idea. The goal is to get it done to do as much as possible and get it as far as you can. And at the end of the quarter, we should all, including me, have like a humble understanding that p-values are complicated and we can always develop our understanding more, if not just to be able to explain it to somebody for my job, right? Whew. Complicated. Okay. Okay. Suppose we were to construct a 95% confidence interval for the average difference between reading and writing scores. And we can do that. We can double check that like by just zipping over to GeoGebra in a second. But when we do it, because we'll double check, should our interval have 0 in it? Yes or no? Or I don't know. Remembering we just got no evidence of any difference on average between reading and writing scores from the hypothesis test, should our estimated average difference confidence interval, should no difference be in there? Yes, no, or this is all still new to me. Hey, Art, we're getting a thumb up. We're getting the thumb up in the participants windows. That's a yeah. Let's just check it. I'm just going to go right over to the confidence interval calculating zone. Yeah, high p-value. So no evidence against the assumption of 0 average difference. Let's switch over to a t estimate of a mean. All the same sample information is there. And looky there, we go from a -1 and 8/10. So that'd be a nearly 2 higher average writing score to a positive about 7/10. That's a nearly a higher average reading score of about 1. So yeah, and 0 is definitely between any negative number and any positive number. So 0 is right there in the interval, not right in the center, but it's there. So it's a yeah. 0 is a completely reasonable value, and we can always just peek at the confidence interval to double check. No problem. And that, oh, look at this timing. It's 10:42. The little kid is still not here, distracting us. And all we need to do is take a participation quiz, and we're out of here with a little extra time for you to be out of the Zoom world and not distracted by a little kid who shows up. Although he's so funny and cute when he shows up, so maybe that's a little sad. But let's go take our participation quiz. Let's go see what it is. Notice I never paused to take it. That means I certainly didn't peek at it before class to see when it would make sense to take it. Quizzes, here we go. Thanks again for having us catch up on all the skipped quizzes before the exam. That was a great move. Let's go for paired data quiz. I've completely forgotten what it's about. Should be familiar once we get past the very boring summary and incredibly boring quiz details and start quiz. Oh, we can analyze the mean of differences using a t-distribution. That's what we did all day. Whenever. Oh, cool. It's a check on the conditions. Which of these conditions look good? You can choose one or even more than one if more than one is correct. Option A, we have independent samples with numerical data. Option B, there are comparable yes-no results for each sample data observation. Option C, sample data has comparable pairs of measurements or counts. Or option D, we have independent samples with ordinal data. I hear something. Someone's coming. Actually, no, and I can tell you now, there's only one correct result there. One's correct. One good one. 3 bad ones. Which ones are stuff we did not do today? Eliminate them. And which one looks like something we did do today? That's the good one. Oh no. There's a little kid hitting me on the butt with a Nerf bat. I didn't even say
It's a
ST.
baseball bat.
I didn't even say ST.
They got the butt. They got the butt. They got the butt with the baseball bat.
Are you singing?
Not Brad saying butt. He got the butt.
He's singing me a Ramones pastiche. Beat on the butt, beat on the butt, beat on the butt with the baseball bat. And he's smiling as he bashes my butt. My child. I've raised him to be a little monstrous butt basher.
I still love you. This is the kid sing.
It's a kid thing. He's not hitting me hard. People get a, did people get a result there? Let's get these done. Independent samples with numerical data. We never did that today. That's bad. Comparable yes, no results. That's not us. That would be in the world of categorical data. Sample data has comparable pairs or measurements. Yeah, that looks pretty good. We did that today, right? Yeah, that's good. Comparable pairs. Hey, that looks great. Check that third one and get your point. That's the good one. Check that, get that one checked. Submit your quiz and you've got your thing. What the last one, I just made that one up out of nowhere. Ordinal data. Oh, wait. Oh.
I want TV.
I see your chat. You're welcome. Good work today, everybody. Someone wants TV because they're home from school. Did you check? Well, all right, I gotta check in on this kid. I will be in contact. If I get sick, I might be home again for Thursday. If I stay well, I'll see you on campus on Thursday, most likely. Just keep a track of your email. And if you have questions, come on by our one-on-one support times or just let me know via email. No stealing, no stealing. He's also trying to steal my wallet. He can't even leave to go to a store. This is ridiculous. All right. Fare thee well, one and all. Have a great afternoon and remaining morning. Bye.
Baseball at your butt.
You should not just throw a baseball at my butt.
Yeah, you're right. I should bat it.
You should